Okay, at the beginning of each of the chapters, I'm going to have learning objectives, the LOs. Okay, so make sure as you go down through here that you pull these concepts out of the notes. Okay, for example, calculate atomic mass and percent natural abundances and isotopic masses. That'll come from the periodic table. Determine the number of protons and neutrons from an isotope. Okay. So these are what I want you to get out of the chapter. Now, if you go to lecture notes, chapter 4 and modules, that's what all this is. Okay, so we're going to be getting into periodic table a lot tonight. From chapter 3, last week we talked about matter is composed of atoms, molecules, electrons, protons, neutrons. There are two kinds of substances. One is called an element, it's called a molecule. Excuse me, an element and a molecule. Okay, the element is basically one thing. One thing like gold, silver, hydrogen, carbon, oxygen, whatever. Those are elements. Those are displayed periodic table. So there's 118 of them as of today. And they all have a unique number of protons, electrons, and a variety of neutrons. From 93 up to 118 are artificially made. And either they stick around a long time or they're gone in nanoseconds, billionths of a second. Some are very unstable, but they're around long enough and reproducible enough that they've actually named them. Now that periodic table up there it's nice and dark, so you can't, let's see if this one's any bigger. Yeah, see, this is a modern periodic table. Notice it goes up to 118. And this one, they actually named them. That's been done in the last 5 to 8 years. They've actually named these from about 111 up to 118. Before that, they were just numbers. They were there, but they were just numbers. Old periodic tables don't even have, like in my Sac City lab, we have a periodic table in there that it's really old. And they don't go up to, goes up to about 111, and then everything is just blank, uneven numbers. So starting right here, these are man-made. This is neptunium. A lot of these are made in fission reactions, an atomic bomb or atomic reactor. And some of them are very, very, very poisonous or radioactive, like plutonium. The stability of anything in this world, or back up, the stability of anything in this universe is measured in something called a half-life. And what a half-life is the time it takes for the original mass to decrease by 50%. So if it decreases quickly, it's unstable. If it decreases extremely slowly, it's very stable. Now, this is one of the enigmas of man-made materials. This guy, plutonium, its half-life is 10,000 years. And it's one of the most deadly chemicals on Earth. And we make it all the time. They weaponized atomic weapons, and they weaponize it with plutonium. Very bad stuff. And we make a ton of it. Nuclear power plants make it as well. Hanford up in Washington State is designed to actually make weaponized plutonium for atomic weapons, but it's bad, bad stuff. Okay, so anyway, this is a list of all the elements, periodic table. That's its function in life. Now, I'm going to talk a lot about the periodic table tonight in terms of how it's organized. There's some trends on it you're going to have to know, some interesting stuff about it. Okay. Now, I want to talk a little about the history of how the atomic model started. Started a long time ago, thousands of years ago. A guy named Democritus came up with a concept called the no-cut theory. The no-cut theory actually talked about if you divide something, let's say we have an apple here, and I cut that in half, is it still an apple? I'm going to take my Jin-Jisu knives out and go. I'm going to go a lot. I'm going to get down to the point where it's no longer an apple. That's what Democritus' concept is. And he called it no cut. And you couldn't cut it anymore, and it still retained the original characteristics of what you started with. Atomos in Greek is no cut. So that's where the word atom comes from. Now, at the time, he had some political, they didn't call it that, but philosophers around. Let's see. These, by the way, are not in your book. Well, dadgummit, a guy named Aristotle came up with some different ideas about matter. His idea was it's made up of only four things. Earth, see now, I don't have my notes, but it's Earth. It's not Earth, Wind, and Fire, that's a group. Earth, water, fire. There's one more. And that stood until 1700s. Because he was more popular than Democritus, and he had a lot more political influence. And you know how political influence is. Okay. Now, during 1700s, 1600s, 1500s, in that time, there were more and more people interested in transmutation. They wanted to take inexpensive metals and turn them into gold. Those were called alchemists, and they did other things as well. But the kings paid them to make gold from lead usually. And the alchemists were very powerful, and they had a lot of shady ways to show that they can make gold. Usually they made iron pyrite, fool's gold, because the kings didn't know the difference. Now, in tonight's lab, actually, is mostly on density, or I should say this week's lab. And that's how they could tell the difference between iron pyrite or fool's gold and real gold, because the density was different. They look very, very similar. Okay, so we had the alchemists running around, and they were trying to find things like the elixir of life. They had this concept of the ether, which breathed life into living things, but they weren't getting paid for that. They were getting paid to make cheap metals into gold. Now, there were some problems at the time. In the 1500s, how was the communication from one village to another? Was that good or bad? Horrible, right? So if one alchemist came up with a method, it was very hard to communicate that process to the village over here, because usually that's by donkey or walking. That's how they communicated, very slow. They had some real issues in those days. Now, why alchemy did not flourish is because of two main reasons. They didn't have a scientific method. Scientific method basically is a way that if I do something, I need to do it in such a way that it's repeatable. So then if she wants to do it, or he wants to do it, you know how. It's on a nice, procedure, step 1, step 2, step 3, results, etc. It's called scientific method. They didn't know about that in those days. So they just did it any old way. Knowledge is power. They frequently did not tell anyone else how to reproduce what they've done, because then that other group would have the same ability to do what they're doing. It lessens their power. The other problem is they didn't use a common language. When we talk about a milliliter in Russia is the same as a milliliter here, at least in the science community. Common language, common measuring, they didn't have that. So that was another reason why it was very difficult then to reproduce these experiments or concepts. So those are the two main challenges alchemists face. Now, this was mostly a European thing also. There was a lot of Muslim scientists doing much better work earlier, like around the turn of the first millennia. In fact, this person here that I can't, does anyone know how to speak Arabic in here? Okay, well, I don't know how to pronounce that. That particular guy is considered many to be the grandfather of modern chemistry. And this was happening like around 1000 AD. Additionally, Asians, Chinese, had all kinds of stuff going on. About the same time as the in the Middle East there. Dyeing techniques, pottery, gunpowder, a lot of medicine. So the main thing on these two slides are all over the world, things were happening concurrently, just not European focused, like most textbooks do. They focus on Western Europe. All right. The first European, Dalton, he came up with the first kind of reasonable atomic theory. Each element is composed of tiny indestructible particles called atoms. So he brought back Democritus's idea of these no-cut little particles. This is kind of interesting. Number two is that you're like, duh. Atoms of a given element have the same mass and other properties distinguish them from atoms of other elements. In other words, gold is not like silver. That's what number two is getting at. Why? Because the atomic structure of those two elements are different. They combine in simple whole number ratios. What's the formula for water? This is a tough one. H2O, right? Okay, yeah. It's not H2.10 or H1.90. It's 2, the integer O. And there's now they hadn't talked much about the innards of the atomic model yet. Along came a guy named Thomson. He discovered there's a negative electrically charged particle within the atom. Now, he didn't say nucleus, he said within the atom. And because the atom was neutral, he figured there had to be something that's opposite of an electron. But he couldn't prove it. He just said it's got to be there because the atom is neutral and electrons are negative. So he kind of back-ended discovery of protons as well. Now, the organization inside the atom was kind of sloppy. He proposed a plum pudding model, which means they're just kind of in there with no organization. No organization, okay? Plum pudding model. Now, one thing in science is you've got to be able to reproduce your theories. So Thomson came up with the idea of the plum pudding model. So that needed to be tested. So Rutherford designed this experiment. This is a very famous experiment. This is a big deal, this experiment. And the plum pudding model, if you were to if we took a real cheap rifle and we were going to shoot into a billiard ball, what would the bullets, now the bullets are cheap. They're not fancy bullets. Let's say they're plastic BB gun bullets, okay? What would those bullets do when they hit that hard plastic billiard ball? Huh? They'd explode, or they would, let's say they were hard enough so they wouldn't explode. What would they do? They'd bounce off, right? Exactly. So Rutherford said, well, I can test Thomson's model by shooting at a really dense atom, gold in this case. And it should, the particles on, this is a ray gun that shoots alpha particles, which is basically 2 protons and 2 neutrons. He shot these particles into that gold foil. And the interesting thing is, if Rutherford model was valid, the alpha particles should bounce off the gold atom. And there's a detector here that would detect where the alpha particles landed after they bounced off. Okay, what happened though is .99% of the bullets went through unimpeded. A very small number of them bounced. So what could you conclude from that? Rutherford was astonished. He was expecting everything to bounce. What? Yeah, there's nothing in there. As he said, you said lots of space, right? Yeah. Nothing is there. It went right through. Now think about this. I'm standing on the floor here. And if these atoms on the floor are nothing, what should I be able to do? Yeah, I'd be in China in a couple minutes. I think China's on the other side, approximately China, but I'm not. So Rutherford's going, what the heck? How can I explain this? And he came up with the idea that because 1% bounced, that there was a small, extremely dense nucleus in the middle. And that 1% of the particles that went through and bounced, that's what they were bouncing off of, is that nucleus. So Rutherford discovered the nucleus. It was very unpopular, however. Now think about this. Now this was 150-ish years ago. And I'm saying to you, person 150 years ago, there's nothing in that atom, nothing, except this tiny, tiny, tiny little marble-sized nucleus. Now let me give you some size comparisons. Let's take a large football field. I'm going to take a marble and put it in the 50-yard line in the middle of that field. That's what kind of sizes we're talking about. So most of the mass, like 99.9% of the mass of that atom, is located in that tiny, 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 tiny nucleus. And the other wild thing is, like charges repel. And guess what's inside the nucleus? Protons, which are positively charged. So you have these particles, positively charged particles, extremely close together. And there's something called a nuclear force that keeps them from flying apart. And when you talk about atomic energy, that's what you're getting into, is that strong, strong nuclear force keeping those protons together. So Rutherford He got a Nobel Prize for something else he's done. But Rutherford, this is a really classic experiment regarding modeling. Okay, so Rutherford is considered, he discovered the nucleus. Okay, this summarizes it all. Okay, and again, dense nucleus is where 99.9% of the mass is. Now, within the nucleus, they discovered there are three kinds of particles. Protons, I just mentioned, they're positively charged. Neutrons are neutral, no charge. And buried within the neutron is an electron and a proton together. So that's within the nucleus. So we have neutrons, protons, electrons, all three. Around the nucleus are electrons only. So most people didn't know that you can have an electron inside the nucleus, but it's buried within a neutron. Now, I want you to look at the sizes of these things. Look at the difference between a proton and an electron. Huge differences in mass, but the charge is equal but opposite. So the charge on an electron is really, really high based on its mass. Protons are much more massive. They have the same charge, only opposite. And neutrons have no charge. And mass-wise, if you notice, if you add up the mass of an electron and the mass of a proton, you'll come up with the mass of a neutron. But they have no charge. Now there's some worksheets I'm gonna have you do where based on a certain element and isotope, we'll talk about an isotope in a minute, you're gonna have to determine how many protons, electrons, and neutrons are in there. And it's a matter of adding them all up and looking at charges and stuff. Okay. Probably already know this, but positive and negatives attract. Like charges repel. And so again, repeating that, what I mentioned before about the protons being inside the nucleus, the positive charges being so close, takes a lot of force to keep them together without flying apart. Okay, now this is something critical. The name of the element is determined by protons, no exceptions. So if the number of protons change, the element changes. And that's not true for electrons or neutrons, only protons. So protons, again, change number. It's no longer that element. So in other words, if we were looking at carbon. Carbon has 6 protons. If it gets one more proton, it becomes nitrogen. Electrons can stay the same, neutrons can stay the same, but if the protons change. Now, when we talk about nuclear chemistry, that happens all the time. It's called transmutation. When we have an atomic bomb, we have uranium, it gets split into krypton, barium, and 3 neutrons. So the number of protons in that uranium, which has 92 protons, gets split in between other elements. And once the protons change, elements change. Okay, so that's really important to remember. Now, what can change but not change the element are electrons and neutrons. Every square in the periodic table looks like this. Okay, there's an integer and a decimal number usually. If there's no decimal number, a number will be in parentheses. The integer is called the atomic number. Its designation is Z. That's also equal to the number of protons. So if the atomic number changes, number of protons change, element changes. Bless you. Always there's an atomic symbol representing the element's name. Some periodic tables will have a name in there as well. So for carbon, they'll have a C and the little word carbon. Sometimes the word carbon is not there. Depends on the atomic or the periodic table. The decimal number has to do with an isotope ratio. And I'll talk about what I mean by that in a minute here. Okay, so this is the minimum information you'll have on periodic table square. Okay, the atomic number, which equals the number of protons, symbol, and the decimal number, which is called the atomic mass. So you have atomic number, atomic mass. They aren't the same thing. And rarely will they be the same number as well. Now, there's a couple elements where that's true, but most of them, like 99% of them, are not equal. Okay, so does that make sense? Okay, a long time ago, about 170-ish years ago, there were two gentlemen in Russia. One was a geologist and one was a physicist. The geologist came up with this idea that of the known elements, there appeared to be a trend with chemical characteristics, like helium and hydrogen chemically act the same. Carbon and nitrogen didn't act the same. And so what he tried to do was to organize this into chemical properties. And one thing they noticed was that the properties started repeating. So if the red circles are elements at the time and the green dots are chemical characteristics, he noticed that all of a sudden, oops. All of a sudden he started noticing that the chemical characteristics started to repeat. So what he did, he went from a one-dimensional train-like model to a two-dimensional model. So what he did is he chopped it off there, and then brought these all together into a two-dimensional table rather than a one-dimensional table. The geologist decided not to publish. The physicist did. His name was Mendeleev, and everyone associates Mendeleev with the discovery of the periodic table. It was really this geologist, but geologists didn't publish. So publish or perish, right? And this is what his periodic table looked like. Kind of hard to understand it, but that's what it looked like. Okay, so this is what a modern periodic table looks like. The only problem with this modern periodic table is there is a shortcut taken for publishing reasons. And right here, all these elements down here fit. into that spot right there. So really, the thing is twice as wide as it looks. So because it was so hard to publish being that wide, what they did is they took out these guys and put them in their own little rows. But we're going to find that that spot there is very important when we start to formulate electronic configurations for all the electrons in the periodic table. That spot is going to come into play big time. Okay. So with a two-dimensional periodic table, there are rows and there are columns. Okay. The columns are distinguished by chemistry. So everything in one column has the same chemical characteristics. The row going across has only one trend. Basically, the size gets smaller as you go from left to right. There are four groups I want you to know. Okay, the first one is the alloy metals. That is this one here. So everything in that column chemically acts the same. So notice we have hydrogen, lithium, sodium, potassium, rubidium, etc. Those all have same characteristics. So if they form an ion, they all form an ion. If they form a +1 ion, they all form a +1 ion. The next group you need to know is the alkali earth metals. Alkali earth metals. And again, chemical characteristics are the same in that column. Halogens on the far right. And lastly, the inert gases or noble gases. And the reason why they have two names is originally they thought that the column on the far right is extremely stable. And they thought it was so stable that nothing would actually bind with it. But later they found that wasn't true, so they renamed it to the noble gases. But you'll, depending on what book you're reading or whatever, you'll see either name. So inert gases or noble gases. Now, I talked about stability a little while ago and last week for that brief time when we were here. Stability rules the universe. There's only one group of elements on this periodic table that's naturally stable, and that's the noble gases. Everything else is unstable in its natural form. So what does it do? Yeah, it combines with something else to become more stable. So unstable goes to stable all the time, never the opposite. And the only way it'll go the opposite way is you apply a ton of energy. So the natural trend, unstable to stable. So we have all these unstable elements. What they want to do, they want to combine with something else to become more stable. Except the noble gases. Now we're going to study electronically why that's so in detail. But for right now, noble gases, very stable. Helium, argon, krypton, xenon, all those, very, very stable. Okay, so you need to know those four groups. Now, every group has got a name, but they're not used very universally at all. These four groups are used all the time. Some of the names that are unrecognizable are Latin or Greek-based, you know, like lead comes from plumbum. Like if you're a plumber, a long time ago, you worked with lead pipe. A plumb bob. Who knows what a plumb bob is? Sort of, yeah. Yeah, they're looking for vertical. It's a weight at the bottom on a string, and it hangs perfectly vertical. So if you want your pipes, your vertical pipes to be vertical, you align it with a plumb bob. Hence the name coming from lead pipes. Iron, Fe. Everyone's heard of ferrous metals, right? Iron metal base. Anyway, the derivation of these names is kind of interesting. Some of them like gold is orium, copper is cuprium. Real interesting how they got derived. Okay. Some of the newer elements are named after either the group or the name of the person that was a principal investigator of the lab that created these. Einsteinium, curium, here's Rutherford. So a lot of times there's Californium, Seaborgium. Seaborg was a physicist from Berkeley. And when I was in graduate school at Davis, we had these graduate seminars once a week. And he would frequently come and visit because I was in a graduate group that did different subjects. We had weed science, food science, environmental toxicology, a whole bunch of different groups in this seminar. So the topics were real interesting. Anyway, he would come. Cool guy. Okay. Here is what Mendeleev looked like. And this is kind of what I was going through before, where we had the elements that had repeating chemical characteristics were grouped together. Okay. Another thing in this chemical characteristics is the formation of an ion. And ions are atoms can either be ions or they can be neutral. If they're neutral, the number of protons is equal to the number of electrons. If the number of protons doesn't equal the number of electrons, then it's an ion. Now, depending on the balance of electrons and protons, you're going to have a positive or negative charge. If there are more protons than electrons, what is the charge of that ion? If we have more protons than electrons, what is the charge of the resulting ion? Positive, because protons are positive, electrons are negative. So the alkali metals form +1 ions. That means they easily lose an electron. And how many electrons do they lose? Yeah. Yeah, then it's one of two types of ions. Okay, if the number of protons are greater than the number of electrons, it's going to be a positive charge. And the name of that ion is going to be a cation. So the alkali metals, the alkali earth metals form cations, all of them. So this group forms a +1, this group forms a +2. The reason why they form the same number is because the chemical characteristics are the same. If the number of electrons is greater than the number of protons, you're going to get the opposite charge or negative. And that's the name of that is going to be an anion. These guys over here form anions, these groups here. Notice this is 0. That means neither an anion or cation forms because it doesn't want to lose or gain electrons because it's fine the way it is. It's super stable the way it is. Everything else wants to lose electrons. Why do you think they want to lose electrons? To become more what? If in doubt, more stable. Okay. Parts of the periodic table. There are 3 parts to the periodic table. Metals. What's the opposite of a metal? A non-metal. And in between a metal and a non-metal, it's called a metalloid. So those are the 3 groups. Okay. There are only a few non-metals. That's the top right corner. Now, on every periodic table, you've got a black wiggly line. That separates the metals from the non-metals. So notice most everything is a metal. We have a few non-metals, and then the ones in between are called metalloids, and there's only a few of those. They're going to be in this purple color. Now in the test, I'm going to give you a periodic table. I'm going to ask you to identify trends. I haven't talked about trends yet. Trends, areas of the periodic table, groups, number of things, okay? All right, so let's look at some properties. Okay, when you think of a metal, what do you usually think of? Yeah, they're shiny, not all the time, but they can be shined. They're bendable. They conduct electricity. So they're definitely some very concrete properties of metals. Non-metals do the opposite. They don't conduct electricity. They don't bend, and they're always dull, and you can't shine them up. Okay, so 3 main properties: conductivity of electricity, bendable, and shiny. And the metalloids are a little of both. Okay, so this just summarizes what I just said. Okay, the metalloids. The metalloids are very peculiar. Metalloids will conduct electricity if you apply a positive charge to it, and they won't conduct electricity if you apply a negative charge to it. That's why they're kind of halfway between the metals and non-metals. Now, metalloids are horrendously important in this world. Does anyone know where the metalloids are used extensively? Say again? Cell phone. And how would you generalize that? You're absolutely right. Right. But just a more general term for all that. Electronics. The transistor was developed in 1947 in Bell Labs in Illinois. And they developed a diode first. Now, the thing about metalloids, Those are wires. So when you put a positive charge on it, they conduct. Negative charge, not conduct. Instead of writing conduct and non-conduct each time, let's represent that with a 1 and a 0. So if it conducts, it's a 1. If it not conducts, it's a 0. What does that look like to you? Binary code. So we can attribute metalloids to the binary code in electronics today, digital electronics. All discovered in the United States, Illinois, by AT&T, the resultant company, used to be called Bell Labs. It's pretty cool. Okay. There are also two main kinds of elements in the periodic table. Well-behaved ones in yellow and non-well-behaved ones in blue. Okay, the blue ones are called transition metals, and they do a lot of different things. The main group ones, 2 on the left, 6 on the right, they are very well behaved. They will always form a +1 cation or +2 cation, where these guys form all kinds of ions all over the place. -1, -2, -3, +3, etc. So those are, the yellow ones are well behaved. And they go by different names. This book uses main group elements, and the transition elements, including the ones below, don't forget about them. And the transition elements tend to be very, a good way to put it, they just behave in lots of different ways. Some ways are more stable than other ways, and we'll talk a little bit about that in this course. Okay, let's see. Now there are two trends I want you to know about, and oops. There are two trends. Where's the trends? All right. Trends are covered further down. So, okay, and I already mentioned when an element loses electrons, it becomes positive, called a cation. When they gain an electron, charge is negative, and they're called anions. And again, these are the groups. Okay, alkali metals, the alkali earth metals. These guys here, the halogens, all form ions, whether they gain or lose electrons. So let me show you how. Okay, so let's look at, let's say, lithium. Now, looking on the periodic table, let me turn the lights up a little bit. Okay, looking on the periodic table on the left, you'll find lithium, Li. What's the atomic number for lithium? 3. So how many protons does lithium have? 3. Three protons. Okay. Now it says lithium likes to form a +1 cation. So if it has 3 protons, how many electrons must it have to form a +1 cation? 2. That's 3 protons means it's a +3. 2 electrons means it's a -2. So we have one more positive proton, hence +1 cation. Okay. So whenever we're looking at the ionic charge, we're looking at protons and electrons, subtracting them. And remember, we can't change protons because that'll change the element. So the only thing we can change are electrons. Electrons come, electrons go. Now I've got some worksheets. If we go to there are 2 worksheets I'd like you to work on. These 2 here. Let me see if that's in modules. Yeah, they're in modules as well. So these 2 worksheets I would like you to work on. And basically, they are you're gonna practice finding the number of electrons, number of protons, figuring out the ions, and also the particular isotope. And we haven't talked about that yet. So let me. Now, the number of protons cannot change. For example, neon here has got 10, but we can have differing numbers of neutrons. And some of these are more stable than others. Okay, so these together are going to make up the mass of the isotope. So an isotope by definition is the number of protons are equal, but the number of neutrons are not. So that means they're isotopes of one another. Okay, so isotopes differ in mass and number of neutrons. The chemistry varies very little. The chemistry is almost identical, almost. It's like it's almost the same, but it's not quite, but it's almost the same. So then how do you distinguish one isotope from the other? You're going to learn 2 ways to do it. We looked at carbon 12 and carbon 14. Carbon 12 means it has 6 protons, 6 neutrons. Carbon 14, 6 protons. Notice the protons are the same because they're both carbon. By definition, it has to have the same number of protons. So carbon 14 would have 6 protons and 8 neutrons. So that number equals protons plus neutrons. So you'll see that written this way. So, and sometimes you'll hear, oh, this is carbon 14 and the atmosphere is changing, or this is carbon 14 dating for for fossils and that kind of stuff. And this is what they're referring to. Carbon-14 has 2 more neutrons than carbon-12. Carbon-12 is the most prolific. The other way you'll see it written is you'll have the symbol. At the top will be this number here, and the bottom will be number of protons. So number of protons, P plus N on the top. You'll see it written both ways. Okay, now that worksheet will talk about these. I'll give you a whole bunch of a big table, and you'll have to fill in the missing numbers, just practicing this. And the other way to write neon here would be so we have the neon 20, 21, 22. The other way to write the isotopes would be like this. Okay, does that make sense? So the superscript, call it the mass number. Remember, the mass comes from only the neutrons and the protons, because electrons weigh so little, they assume they weigh nothing, but they don't. They weigh something, but they don't include them in that mass number. It's also an integer. The bottom number is the atomic number, or Z, and that's the number of protons. Okay, let's see here. Now, the relative abundances of isotopes vary tremendously. Some isotopes are very, very stable. Other ones aren't. When you get into nuclear chemistry, you look at the proton and neutron ratios, and there's some that are preferred over others. So the ones that are preferred tend to be more abundant. Other ones, you'll find the isotope is extremely common. It just varies all over the place. Now, when you look at the percent abundance, that has to do with how they calculate the atomic mass, that decimal number. How are we doing on time? Let's see, it is 6:02. I'm going to go over this Thursday because we have to talk about something called a weighted average, and I think I'm not going to have enough time. Okay, so we've covered a lot of stuff on this periodic table. And if we go back to the original slide on the student learning outcomes, we've done 1 through 9. And those 2 worksheets I want you to do, one is on neutral atoms, the other is on an ion, all ions. Okay, so we've gone through these guys. So the periodic table we're going to use in the rest of the semester. We'll be using it all the time. So I'm going to be talking about it a lot, so we'll become much more familiar with it. So if you've never had chemistry before, this may seem a little obtuse, but if you, hopefully it's a review for you. Okay, so that's it for tonight. So the Tuesday lab people, I'm going to want to look at your pre-lab for tonight, for lab 3. And again, I'm giving you some leeway on lab 3. Normally, if you don't have your pre-lab done, you can't do the lab. You have to go home. All right. Except for tonight.